There we go. So our next presenter is Allison Koenecke. I realized I forgot to ask you about your surname. I'm very sorry. So Allison is at Microsoft Research New England and is an incoming assistant professor at Cornell for information science. So thank you very much, Allison.
Oh, thanks for having me. So great slate of presentations we've had today, and today I'll be speaking more on the causal inference side of things. So I guess piggybacking off a lot of the work we've seen already, a lot of it is focused on ML, which has kind of this broad universal concept of trained validation test sets, and splitting your data sets in machine learning to ensure you don't overfit your models. But this wasn't really historically something that was done in causal inference land. And so there's less of a universally accepted way of ensuring external validity, for example. And of course, there are lots of exceptions in causal work today. So things like Susan Athey's work on honest causal random forests to prevent overfitting. But it's hard to say that there is a broader framework for causal inference reproducibility as is. And meanwhile, kind of instead of observational causal analyses, which is most of what I'll be talking about today, you can run RCTs, as is done in, say, clinical settings. And those are very well scoped and easy to replicate. I say easy, following the, Brown Policy Lab stuff where, I guess we'll hand wave when we say easy to replicate, but, relatively easier to replicate, maybe because all of the steps are written down, especially for these clinical trials where everything is very cleanly written, but RCTs are super costly to run. And so given that we're thinking about causal inference today in this talk, how do we ensure reproducibility, spanning both reproducibility in other observational data or studies, and also potential reproducibility in RCTs themselves. So today, going more into the definition of the title of this talk, what are retrospective analyses? Today, I'll be talking specifically about ones where the treatment is a specific drug, which makes this a pharmacoepidemiological analysis. Boom, nailed it, first try. And so a retrospective analysis is one where you take existing data that contains both exposed and unexposed patients, also known as treated and control, right? And then you look at their outcomes in the existing data that have already occurred. And so this is nice because if you have a robust data set, you have plenty of covariates in your data, you have a lot of control over what features to include, and it's cheaper to, in theory, run some regressions in R than it is to run a full RCT. But the question still remains of how to actually do a replicable analysis for retrospective data. So the paper that I'll be talking about today is a how-to guide on doing reproducible causal inference via retrospective observational analysis. And so I will go through 10 simple rules that span across 4 different phases. I will say each of these simple rules could probably be like multiple papers or already exists as hundreds of different papers. So, 10 simple rules, take it with a grain of salt. And before going through the rules, I'll introduce our specific running example, which is a pharmacoepidemiological example. And as with a lot of work in the field lately, this is a COVID-related research. And the idea here is that patients with COVID, and likewise for patients with pneumonia, are at risk of cytokine storms occurring. You don't need to know the details of this, but this ends up leading to respiratory distress, and in particular resulting in patients being ventilated and in some cases dying. So now we know from previous work, there is a specific drug called prazosin that has a protective effect on mice. And so this means that the mice that have this information don't end up reaching the cytokine storm phase. And so given that there seems to be some mechanistic reason for prazosin to work, as in this isn't some random guess of a drug, there is like a biological reason for this to happen, do we think the same protective effect actually exists for humans? And in particular, we're going to be talking a lot about what we call alpha blockers, which is the class of drugs that prazosin belongs to. So going back to our 10 simple rules, let's start with the guiding principles. So zooming in on these, our first 3 rules start here. First, for our particular example, which is based on real life, we ended up with like 4 or 5 different papers related to this whole line of research. We had a team of epidemiologists, computer scientists, economists, biostats, people, medical practitioners. And for us and for this type of work broadly, it's really important to lay the groundwork so you have folks who are able to both deeply understand the medical implications of this sort of pharmacoepidemiological study, and also folks who deeply understand causal analysis. So second is to emulate an RCT. Now, this isn't just helpful in the sense of, if you want to reproduce this eventually and actually run an RCT, if you were to get the funds for it, it's also helpful just for yourself to diagram out what exact comparison you want to study before even thinking about what data to use. And so the way RCTs tend to be modeled in the health literature is with what's called a consort diagram. So this is an example of a consort diagram. I'll go through the specifics of what we've written in these limitations later. But for now, let's just focus on the key fact that we can glean from making this sort of diagram, which is that we can diagram specifically what we would be doing if we ran an RCT, including recruitment for treatment and control groups. So in particular, we have up on top inclusion/exclusion criteria for getting into a clinical trial. Next, we split into treatment and control, where alpha blockers, again, is the class of drugs that we're studying. And here we're listing two outcomes where a patient might get ventilated and then die. So each of these outcomes is a binary variable. So now with that idealized RCT in mind, the third rule involves just letting go of all of your expectations because nothing is perfect and this too will not be perfect. So how do we proceed given that we know that doing this exact RCT is basically impossible? Now zooming out of our guiding principles phase, let's move into the preparation phase. So the next four rules kind of focus on the hypothesis at hand. So we'll start by formulating the research goal. So for our sorts of studies, there are a few different dimensions in particular that are important to think about with regard to drugs. So we've been talking a lot about this drug, prazosin or alpha blockers as a treatment, but how do we quantify that? So an obvious one is the quantity. So, okay, how many milligrams is the patient taking? But then how do we know if the patient is actually taking the drug? What if the patient, just started the drug and then had only taken one dose before being ventilated? Then we probably don't actually trust that effect would be due to the drug. So things like duration and frequency and recency of exposure are all important to consider. And similarly, we include tips for other kind of major points to establish. So for example, defining exposed groups and unexposed groups in detailed ways. So let's say that our definition of exposure is we want to ensure patients taken more than, say, 180 days of alpha blocker drugs in the past year. So conversely, do we want our unexposed definition to be, our patient has taken fewer than 180 days of that particular drug, or should it be instead someone who's never been prescribed that drug? So these sorts of decisions are all really important to write down right from the start. So similar thing for outcomes, we need them to be measurable and specific. And all of these should come together when you're thinking about your hypothesis, including whether you want to consider multiple exposures or outcomes. And so as a quick example, we've now developed our hypothesis from earlier in this talk, which was just, do alpha blockers improve patient outcomes? So now we can ask a more measurable question, which specifies the treatment and outcome. All right, so now that we've thought about specific exposures and outcomes, let's talk about confounders, because after all, this is in theory a causal inference talk. So as we've discussed, the main hypothesis we're trying to study involves the effect of alpha blockers on two of our outcomes of interest. But we need to observe and adjust for confounders, right? So there are a few conditions that we want to satisfy in causal analyses. So for example, firstly, we need treatment assignments to be independent of individual treatment effects. So we want unconfoundedness. And also we want our treatment assignment probabilities to be strictly between 0 and 1. That's called overlap. We will talk about overlap in a few slides. So for now, let's just focus on confoundedness. So in order to say anything about this particular treatment effect, in order to satisfy the unconfoundedness condition, we need to adjust for confounders. And so one obvious set of confounders is patient comorbidities, right? So these are things like COPD or hypertension, diabetes, the number of hospital or doctor visits. The intuition here is that the sicker someone is overall, the more likely they are to be taking a bunch of drugs like alpha blockers, but also the more likely they are to get ventilated or die just because they've historically been very ill. So as part of our thought process, we need to keep track of what we expect are confounders that we can see that are observable. I'll talk about unobserved confounders towards the end of this talk. But for now, the idea is let's just think about what confounders we need to worry about. And zooming out a bit here now, since we figured out what specifically we want to measure, I'll talk about, finally, per the title of this talk, what a retrospective cohort study is. So this is a specific method that we've used to perform our causal analysis on our historical observational data. Recall that we still haven't actually talked about getting data yet as part of our 10-step process. So this is all on some ideal imaginary data. So to start, let's say that we have some historical patient data, and for a specific patient, we see that they are admitted to some hospital on January 1st, 2021 with a COVID diagnostic code. Now what we can do is look backwards for a year of that patient's data and ask a few questions. So for example, in the past year, first let's generate a binary treatment variable based on the patient's alpha blocker supply. And we'll also generate some variables speaking to the patient's overall health in the past year. So questions 2 and 3 are basically tackling things like the observed confounders that we just reasoned about. And meanwhile, going back to this 2021 inpatient admission timeframe, which is also something you need to define, right? So this can be either just the amount of time that they're in the hospital, it could be 28 days, so a month-long observation timeframe. Within that patient admission, we then ask a few more questions. So in our case, 2 binary variables. Does the patient get mechanically ventilated? And then does the patient die? So that's basically how we think about the retrospective cohort study. And this is how we end up with our nice tabular data that we can then use to run regressions and that sort of thing, right? So now that we've listed out some potential confounders and talked about how they fit into this like broader retrospective analysis plan, we want to figure out the target population. So recall that with the consort diagrams that we thought about in the context of making our ideal RCTs, this is like the shared inclusion-exclusion criteria at the top across both arms. And so adding a few more emojis on this diagram from a few slides ago. So here's another trait that's a confounder, but that I'll also talk about as a target population, which is gender stratification. So fun fact, in the United States, most prescriptions of alpha blockers are for men, in particular men aged 45 plus who have benign prostatic hyperplasia, BPH. And this is a condition that's clinically unrelated to respiratory problems. So this also ties into needing an interdisciplinary team, since knowing that fact requires a medical doctor on board, right? So going back to BPH, prostate problems tend to worsen with age. So treated patients are generally older, meaning that we want to include age as an observed confounder too. So now we need to think about a specific trade-off that we have to make in our study design, right? So if we restrict our study to older men, this reduces unobserved confounding, but we're now sacrificing external validity. So our results probably won't extrapolate to the general population. And in general, this is an important step to think about when refining your target population. So how will your internal validity be impacted versus your external validity? And lastly, we keep mentioning COVID patients, right? Like that's our kind of motivating thing in this talk. And so one question when defining the target population in particular is how do we actually define a COVID patient? So we actually started doing this work in March 2020. And for the first 60-ish days of the pandemic, there actually wasn't an official diagnostic code in the US for COVID. So the CDC only actually announced the code in like April 2020-ish. So early in the pandemic, COVID tests were only available in inpatient environments and were reserved for like the sickest patients. So we had a ton of unobserved, undiagnosed patients. And we can't estimate the treatment effect in that early 2020 undiagnosed population since we never actually get to observe a qualifying condition of a COVID diagnosis. So later, once COVID actually gets its own diagnostic code, we face another issue, which is that you have a bunch of diagnoses made across communities, but those results might not actually appear in a patient's health records or claims history, especially if they're milder cases. And so if we want to talk about COVID patients as a target population, we need to make some limitations clear. So for example, we might be limited to only severe cases of COVID warranting hospitalization in a certain time frame. And for our case in particular, for robustness and reproducibility, we actually consider 2 differently defined COVID cohorts. So one uses a formal diagnosis with an actual inpatient diagnostic code. And the other one uses a suspected diagnosis heuristic. So that's again formed by the clinician side of our team based on symptom review. So all this to say, defining target population, very important. So now that we've thought about the specifics of all of these exposure definitions, outcome definitions, that sort of thing, only now at the end of the preparation phase do we ask you to turn to the idea of figuring out what your data are. So as far as data sets go, the first thing to do is to make sure you actually know what's in your data. And this is where something like data sheets for data sets comes in handy. where it's actually listed out what the data origins are, so data collection methods, limitations, and that sort of thing. It's also important to have domain experts in the loop here to ensure that the domain-specific standards seem correct in the data. And so as a quick example, here are two age histograms from two data sets that we actually used. So we ended up using medical claims data in order to run these analyses. And hopefully just looking at these makes you wonder what's going on. So we recognized very early on that the market scan data on the left has a Medicare data exclusion, meaning that we don't have anyone over the age of 65 in that data set for what turns out to be a very reasonable reason. So make sure that you understand what's going on in your data. And now that we've finished the preparation phase, we can move on to the analysis planning phase. All right, so there are just two rules in this phase, and let's start with the exploration rule focusing on surrogate outcomes. So a key tenet here is to use surrogate outcomes to keep yourself from being influenced by partial results as you're working on the analysis. It's also important to keep good records of how you permuted or generated your outcomes for broader reproducibility. Don't worry, you will use your actual data at some point in a later step. But for now, now that you've masked yourself a bit, what do? You do what you would otherwise do in most other analyses, which is start to look at your variables of interest. So this can be looking at covariate distributions by various data cuts to understand your data, check for any inconsistencies. And next, recall that for a causal analysis, we want to have unconfoundedness and also overlap. We already talked about confounders, but not much about overlap yet. So overlap means that there is a distributional overlap between individuals being put in both exposed and unexposed groups. This is something you don't need to worry about if you're just running an RCT, because each patient enrolled in the trial is randomly assigned to treatment or control. Caveat, everything that the policy lab folks already talked about, where maybe they are not perfectly enrolled, but that aside, you do need to worry about this a bit more with observational data. Because maybe treatment is chosen by some predeterministic policy. So like super sick people necessarily all get treated, which means they're not comparable to the untreated group. So what does better empirical overlap mean? This is based on propensity scores, which reflect the probability that an individual actually receives treatment, i.e. belongs to the exposed group on the basis of your observed covariates. And so if you compute each individual's propensity for treatment, you can use propensity trimming to ensure that neither exposed nor unexposed groups have any crazy outliers with like less than 0.001 or more than 0.999 probability of being assigned to treatment, which would be unattainable in the other exposure group. So now to counteract confounding by indication, which is how medical people say confounding, a bunch of analytical techniques use propensity scores to balance exposed and unexposed groups by matching patients or by weighting using propensity scores. So the latter would involve assigning more weight to the unexposed individuals who appear more similar to exposed individuals in terms of the observed covariates. And the next tip is to keep it simple, stupid. So just start with a very basic unadjusted model as your baseline before throwing in the kitchen sink or doing fancy machine learning stuff. And after doing these 5 steps, go ahead and throw in all the bells and whistles. So putting this all together for our particular study, we used the R package GRF to estimate propensity scores. Then we propensity trimmed our sample to retain the overlapping region such that between the exposed and unexposed propensity score distributions, we kept scores above the maximum of the 2 distributions' first percentiles and below the minimum of the 2 distributions' 99th percentiles. And then with that remaining subsample of data, we can do unadjusted analysis of the exposure outcome relationship with, say, like a Fisher's test. For matching, you can use the R package match it. For our particular use case, we did 5-to-1 Mahalanobis matching. So that involves finding 5 unique unexposed matches for each exposed patient. And for another adjusted model, we ran an IPW, an inverse propensity weighted logistic regression using the R package survey. So it is very convenient that across the board on our team, everyone was happy to use R, but of course your mileage may vary. So with all of this stuff going on, as far as IPW and matching go, how do we actually know that we achieve covariate balance? A very important part of this kind of refinement of the analysis plan is doing things like covariant balance checking. So here we visualize the standardized differences of means for included covariates. So here, this is a type of plot called a love plot, shows the standardized mean differences in covariance like patient characteristics before versus after matching. So you see that between the exposed and unexposed groups, they had much more different covariates with the red dots pre-matching and much closer to zero difference with the blue dots. So this is all good signs. And now for our penultimate rule, after running our unadjusted and adjusted analyses, we include sensitivity analyses. So the first is the kind of usual type of robustness check that you might do. So figuring out, what type of hyperparameter tuning makes sense to do, whether results change a ton with the inclusion or exclusion of a bunch of different covariates, that sort of thing. And as far as modeling techniques go, you can try a range of estimation approaches, right? So for example, for doubly robust methods, you can use a bunch of different machine learning methods to estimate propensity scores and your outcome models. And the point here is to see whether your obtained treatment effects are sensitive to the specific methods that you choose to employ in your kind of main analysis. Next, we need to think about unobserved confounding. So while there's no way to test for unobserved confounding directly, since you don't know what you can't actually see, there are ways to estimate basically how strongly correlated your hypothetical unobserved confounder would have to be with the exposure or outcome or both in order to move the estimated treatment to the null. So basically, how hard would it be to flip any significant treatment effect that you find over to having no effect at all? So then you can make some supporting claims about how likely it is that such a confounder might exist and is either unknown or unmeasurable. And one way to do this to assess this metric of unobserved confounding is with the e-value. And finally, you can consider coming up with some negative outcome or treatment control experiments, which are similar concepts to running placebo checks in kind of the broader causal literature. So in a negative outcome experiment, you run your treatment on a fake outcome not associated with the treatment, where you should find no treatment effect. In a treatment control experiment, you kind of do the opposite. You run a different treatment with no known connection to that outcome on your true outcome. And again, you should observe no protective effect. So if any beneficial effect is found in either test, then there is some unobserved confounding somewhere, which may help you reason about point number 2 that we just talked about. So with that, we've finished our kind of analysis planning phase, and we go to our final phase with just one rule, and this is the execution phase. So here we'll actually run the analysis and talk about sharing results. So first, it's time to finally use your real data. Recall that everything before was run on your permuted outcomes or synthetic data. So here you finally rerun your unadjusted and adjusted analyses and look at the real results. Next, if you run into issues because of your true data, so maybe you need adjustments in your propensity trimming or something, of course, refinements can be made. It's good to pre-register those as well, where OSF is more the physical sciences side as predicted, more the social sciences side, all of these types of platforms, fairly straightforward to use. Next is to make sure to present your results in a way that is unsurprising to your audience, right? So for us, our statistic of interest is the odds ratio, which is hopefully familiar to people across both medicine and causal inference. So we define R null as the odds ratio equals 1. So the exposure does not change the odds of the outcome occurring. And then we assess the drug to be beneficial, to have a protective effect if we find that the odds ratio is less than 1. Next, when reporting results, you want to make sure to describe all of your limitations. So for example, in our case, we want to make clear that our results are for, say, older men in the US with official COVID diagnoses. And lastly, make everything easily reproducible, which other people at this conference have talked about far better than I probably will. And so that means, writing your methods clearly step by step. Even if your data are private, you might still be able to upload your code and documentation. For us, publication venues like eLife in the life sciences are also great for reproducibility in terms of publishing, the back and forth of the review process as well. And so putting this all together, what do our final figures look like? As mentioned, we report the odds ratios and corresponding confidence intervals, finding that alpha blockers writ large, which are these kind of dark green lines, and in particular doxazosin, which is the light green lines, they all have a protective effect in that the odds ratios are all less than 1. And for robustness, this forest plot is what we call this, shows similar results for 2 different definitions of death. So both within that particular inpatient admission and also within that month. We also include, results across 3 different types of analyses, including our 2 adjusted models accounting for confounders. And so overall, that was just a set of examples on how to actually use our 10 rules for reproducible retrospective causal analysis. So as I mentioned at the very beginning, there are lots of reasons to do this observational work, especially because RCTs are expensive. That said, one bonus of our doing this COVID-related observational study is that it actually did result in us getting funded to run a clinical trial. So that's in the works now, and will hopefully serve as an external source of replication for our work. And separately, I want to note that it's relatively low-hanging fruit to get significant results, but it's much harder to actually do a good causal inference study, right? So these principles can be used for easy reproducibility of the specific hypotheses that you're studying. But that said, there is no like one-size-fits-all method to generate all causal analyses. This can't be fully automated. For example, you should still have a mechanistic reason to actually think that certain drugs should be studied. But while full automation might not be ideal, given the importance of domain expertise and having domain experts on your team, there are still plenty of useful tools for data scientists hoping to have kind of this causal inference pipeline tool at their disposal. So this Python library, do-y, and corresponding user interface, show-y, can be used for a ton of applications spanning healthcare and business intelligence to conduct things like retrospective analyses. And the plot I'm showing at the right is a super handy tool that allows the user to kind of conveniently compare treatment effects across a bunch of different adjusted methods and models. So here we have, IPW. You can include a bunch of different specifications with different covariates included. And so this really speeds up the manual process of comparing across different analyses. All right, so with that, I will stop and take questions, but here's the name of the paper I went through today, which I think Rohan already linked very helpfully. This paper was led by Mike Powell, and feel free to reach out if you have any questions about this or any of the follow-on studies that we did using retrospective analyses.
Thank you very much, Allison. If anyone has any questions, please feel free to raise your hand and I'll call on you. I'll just get us started with, do you see much role for DAGs in causal analysis?
Yeah,
or are you, yeah.
Great question. Here's the next slide in my supplementary material is in fact a DAG.
Sorry.
We do find them super useful in reasoning about these things. I did skip it in kind of the condensed version of the 10 simple rules because it takes a while to kind of stare at this picture and internalize it more. But very similarly to how we thought about confounders, right? Of course, you have many more arrows to consider when you are actually looking at what sorts of interactions you might consider across different drugs. You have a bunch of things like drug allergies that maybe you might at first think are important, but actually they aren't really. So, drawing out DAGs, very helpful. Big fan. Yeah.
That was completely not set up for anyone. Does anyone have any other questions or comments?
I guess one quick question I had was, this is fascinating and wonderful, and I've already sent the PDF to my students, so thank you. In regards to DAGs, in addition to the graphical displays, are you thinking about doing things like using frontier criterion instead of controlling for confounders, or really using the do calculus in order to try to address some of the problems of confounding? I have not seen that in the this kind of style of work myself. I've seen graphs like this, but not actually the do calculus in action.
Right. So do-y is great for all of the do calculus stuff. I will say that for our work on this, it is pretty, we don't actually use any of the do calculus programming type of stuff. We just kind of stick to the standard cookie cutter tools, run some causal forests, that sort of thing.
Are there any other questions or comments? Have you taken this approach in social sciences? I mean, this is very much, medicine and things like that. Do you have research interests in social sciences as well, where this could be applied?
Sure. So for me personally, a lot of my work is actually in kind of fairness in online applications. And so I've done plenty of work with, say, for example, propensity matching as kind of a means to an end in social sciences. But to kind of shill for this paper as part of my answer. I hope that I and others will start using these 10 simple rules more broadly in the social sciences, because I do think it is kind of like you think of it as a means to an end and not really more specifically as a key component to the overall analysis. And so hopefully this paper helps with that.
Yeah, I just feel like we need to combine all the past 3 presentations into one like super research. Any other questions or comments? Well, we might just say thank you once again to Allison. One of our presenters yesterday, Lars, is at Cornell also. So when you actually move there, or we'll have to do email introductions or something. So thank you very much for your presentation. Really appreciate it.
Thank you.